Astronomers were preparing for a routine observation when an unexpected signal from deep space immediately captured global attention. The discovery began with a faint anomaly detected by a space telescope studying distant exoplanets. Initial readings suggested energy fluctuations inconsistent with any previously recorded cosmic activity. Scientists quickly cross-checked the data to ensure there were no technical errors or interference from Earth-based instruments. After multiple confirmations, it became clear that the signal represented something entirely new in observational astronomy. The anomaly appeared to originate from a star system previously considered ordinary and well-documented. Early reports hinted at the possibility of a previously unknown celestial body or an unusual natural phenomenon. Researchers shared preliminary findings with international observatories, sparking collaborative investigations across multiple continents. The signal's pattern was irregular yet organized, challenging existing models of cosmic behavior. Social media buzzed with speculation, but scientists emphasized that conclusions must be drawn carefully. Observatories around the world immediately adjusted their schedules to focus on the unexpected source of energy. Instruments designed for studying exoplanet atmospheres detected minute shifts in radiation. Initial theories suggested interactions between previously unidentified magnetic fields could produce the irregular signal. Teams conducted simulations to test whether natural stellar phenomena could explain the anomaly without invoking unknown physics. Each simulation confirmed that existing models could not fully account for the data observed. A high-priority research group was formed to coordinate global monitoring and data analysis. Within days, additional telescopes reported subtle variations, matching the original signal, confirming it was not an isolated measurement error. Scientists noted the signal's consistency over time, a characteristic rarely seen in such distant observations. The discovery sparked cautious excitement, highlighting the universe's capacity to surprise even experienced researchers. Media coverage, focused on the mystery while ensuring explanations, remained rooted in science and observation. Scholars emphasized that unexpected discoveries like this often lead to breakthroughs in understanding cosmic evolution. The energy emissions did not match patterns associated with known stellar phenomena like pulsars or supernova remnants. Early data analysis suggested that the source might be a compact object interacting with its surroundings in unprecedented ways. Research teams began examining historical telescope archives for overlooked data that might correlate with the current anomaly. Surprisingly, minor signals from decades earlier bore faint resemblance to the current discovery but were previously dismissed as noise. Analysts carefully compared archived data, noting subtle similarities that suggested the phenomenon had existed for years. Coordinated international efforts aimed to predict the anomaly's behavior and determine its potential impact on nearby celestial bodies. Astrophysicists debated whether gravitational interactions, unknown material compositions, or other factors could produce the observed signals. Each hypothesis was tested rigorously, with simulations iterating over thousands of possible scenarios. Observatories scheduled long-term monitoring campaigns to track energy emissions with precision instruments. Data from radio, optical, and X-ray telescopes were combined to provide a multidimensional view of the phenomenon. Researchers noted unexpected correlations between the signal and subtle variations in nearby interstellar gas clouds. These correlations hinted at a complex interaction between the source and its cosmic environment. Scientists cautioned that interpretation required careful analysis to avoid jumping to conclusions unsupported by evidence. Laboratory experiments simulated conditions found near the anomaly to test known physical laws in extreme environments. The experiments confirmed that certain behaviors observed in space could not be fully replicated on Earth. This further fueled curiosity and reinforced the uniqueness of the discovery. Early theoretical models suggested that the anomaly might challenge conventional understanding of star system formation. Peer-reviewed journals prepared initial reports to document observations and methods for independent verification. International teams collaborated to maintain transparency while protecting the integrity of ongoing research. The discovery became a topic of conferences, webinars, and public lectures emphasizing scientific curiosity. As telescopes worldwide focused on the anomaly, scientists began noticing subtle patterns in the energy fluctuations. The signal displayed a rhythmic consistency unlike any known pulsar or stellar oscillation. Initial theories considered gravitational interactions with nearby celestial bodies, but calculations failed to fully explain the observed energy output. Researchers used advanced simulations to explore possibilities, testing hundreds of scenarios. Surprisingly, none of the conventional models matched all characteristics observed in the anomaly, suggesting unknown processes at work. Satellite instruments detected correlated shifts in interstellar gas, implying the phenomenon might influence its environment. Scientists confirmed these shifts were subtle but consistent, reinforcing the legitimacy of the initial discovery. The discovery prompted a review of historical telescope data, revealing minor unexplained signals. Researchers concluded the phenomenon may have persisted unnoticed for decades, invisible without modern detection methods. Collaborative efforts increased, with observatories coordinating observation schedules to capture continuous data over several weeks. Data streams were analyzed simultaneously in multiple wavelengths, including optical, radio, and X-ray, for a complete picture. Analysts discovered minor correlations between the energy emissions and variations in nearby interstellar dust density. These correlations suggested that the anomaly might interact dynamically with its surrounding cosmic medium. Laboratory physicists attempted to replicate aspects of the phenomenon using extreme simulation chambers. The partial replication underscored the anomaly's uniqueness and complexity beyond terrestrial conditions. Scientists cautiously avoided speculative interpretations, emphasizing evidence-driven analysis of observed behavior. Peer-reviewed journals prepared detailed reports documenting methods, ensuring transparency and reproducibility. Preliminary findings suggested a previously unknown class of celestial object could explain the unusual signals. Discussions at conferences focused on the importance of rigorous verification and the potential implications for astrophysics. The anomaly challenged existing theories of stellar evolution and energy emission patterns. Graduate students and early career researchers were invited to contribute fresh ideas and modeling approaches. Simulations incorporating novel variables indicated potential interactions with weak magnetic fields and interstellar plasma. While promising, these models required extensive validation through continued observation and data collection. Observatories coordinated internationally to track minute changes in the signal over time, refining predictions. Real-time data sharing allowed teams to compare results across geographic regions, improving reliability. Observers noted slight variations in intensity that might suggest a slow evolution of the phenomenon. Scientists emphasized that these small changes required months of continuous monitoring for meaningful interpretation. Public interest grew responsibly, with updates framed around scientific exploration and the thrill of discovery. Popular science platforms shared visuals and explanations without exaggeration, encouraging curiosity over sensationalism. Researchers remained careful to distinguish verified findings from speculative hypotheses in all communications. Advanced computational models were developed to simulate possible particle interactions within the observed system. Preliminary results hinted at the presence of unknown physical mechanisms affecting energy propagation. The discovery highlighted the universe's capacity to surprise even the most experienced astronomers. Observatories conducted repeated cross-validation to confirm the accuracy of measurements and rule out instrumentation errors. Each observation brought incremental understanding while revealing new questions, illustrating the iterative nature of science. Scientists underscored the importance of patience, as unraveling the phenomenon would take years of meticulous work. The anomaly's persistence emphasized the need for ongoing monitoring and archival review to detect subtle cosmic events. Teams explored whether similar anomalies might exist in other star systems, using refined detection criteria. This broader search aimed to determine whether the phenomenon was unique or part of a class of unknown objects. Initial comparisons suggested its rarity, increasing the significance of the discovery. Researchers carefully documented every detail, ensuring future reporting and continuity in the research process. As data accumulated, I began noticing a subtle but consistent energy modulation. This modulation repeated over hours, suggesting a regularity that differed from typical cycles. I ruled out interference from known sources, confirming the signal's authenticity. Advanced telescopes detected slight gravitational effects in the surrounding region. This observation sparked discussions about whether the anomaly represented a new type of object. I combined multiple data types to build a multidimensional model of the anomaly. Early models suggested the object interacted with local interstellar gas and dust. Observations revealed minute shifts in radiation patterns, possibly indicating internal processes. Simulation teams tested hundreds of potential scenarios to match observed fluctuations. None of the conventional astrophysical models fully accounted for the combined energy patterns. The anomaly's uniqueness prompted international collaboration among observatories. Verification and careful documentation became vital to avoid premature conclusions. Cross-referencing historic data revealed faint hints of similar activities from decades earlier. I noted slight patterns that aligned with the current anomaly. Observatories scheduled long-duration monitoring campaigns to capture gradual changes. The anomaly displayed consistent behavior across different instruments, reinforcing its validity. Minor variations in intensity suggested the phenomenon might be dynamic and evolving. Laboratory simulations attempted to replicate conditions, highlighting the phenomenon's complexity. I maintained strict focus on evidence-based analysis, steering clear of speculation. Conferences and webinars explored theoretical implications, emphasizing scientific rigor. Early discussions proposed a new classification for celestial objects with similar energy patterns. Simulations incorporating weak magnetic fields produced partial matches, guiding further strategies. Citizen science projects launched allowed volunteers to assist in pattern identification. I noted correlations between the anomaly's fluctuations and surrounding cosmic dust density. Scientists cautioned that interpretations remained provisional, pending long-term observational data. Real-time collaboration allowed teams to compare readings, increasing measurement confidence. Modeling indicated that the phenomenon might challenge existing theories of star system evolution. Such unexpected findings illustrate the universe's inherent complexity. Each new observation was logged carefully for reproducibility in future studies. Minor gravitational effects hinted at the possibility of unseen companions or anomalies. I tested whether these fluctuations could be caused by known physics, finding inconsistencies. The object's persistence indicated it had likely been undetected due to previous limitations. I highlighted the importance of continued observation to uncover subtle cosmic phenomena. Public engagement encouraged curiosity and scientific explanation, avoiding speculation. Updates shared in educational programs focused on methodology, observation, and discovery. Computational models were refined to incorporate interstellar plasma and dust clouds. Preliminary findings suggested energy modulation mechanisms not previously recognized. Observatories continued monitoring across multiple bands to ensure comprehensive coverage. Cross-validation between instruments confirmed readings were consistent and reproducible. I began publishing preliminary reports in peer-reviewed journals to document results. This transparency allowed independent verification while safeguarding ongoing analysis. Early interpretations suggested a new type of object producing detectable energy patterns. Continuous monitoring revealed that the anomaly emitted energy in subtle pulses, with slight variations that suggested a previously unobserved natural process in space. Researchers carefully analyzed these pulses, noting consistency across different instruments and wavelengths, which confirmed the signal was genuine. The object appeared to interact with its surrounding environment, including nearby gas clouds and interstellar dust, in measurable ways. Advanced simulations suggested these interactions could provide clues about the object's composition or structure. Historical data review revealed faint traces of similar patterns, suggesting the phenomenon may have existed for decades unnoticed. Scientists stressed that these earlier signals were weak, but aligned with the newly observed behavior, providing continuity in the data set. Teams collaborated internationally, sharing real-time data to ensure verification and avoid misinterpretation of results. Observatories synchronized measurements to capture subtle changes in the object's energy output over time. Small fluctuations suggested the phenomenon might be dynamic, slowly evolving, rather than static. The energy pulses did not correspond to known stellar oscillations or typical pulsar patterns. Researchers explored whether weak magnetic fields or interactions with surrounding matter could explain the observed effects. Models indicated that standard astrophysical theories could not fully account for the combination of rhythmic energy and environmental interaction. Scientists emphasized that the phenomenon did not imply anything beyond natural processes, avoiding speculation about artificial origins. Laboratory experiments simulated extreme conditions to test theories, though only partial replication was possible on Earth. Citizen science programs allowed enthusiasts to assist in pattern recognition under professional supervision. These programs highlighted how responsible public engagement can contribute to verified research. The anomaly's discovery encouraged broader searches for similar phenomena in other star systems using refined detection criteria. Early comparisons suggested that while rare, similar signals may exist elsewhere, awaiting technological capabilities to detect them. Researchers documented every step meticulously to maintain reproducibility and reliability for future studies. Cross-validation across different observatories confirmed the signal's consistency and eliminated the possibility of local interference. Observations revealed subtle gravitational effects on surrounding material, offering hints about the object's mass distribution. Simulations incorporating these effects suggested complex internal dynamics not accounted for in conventional models. Public updates emphasized scientific curiosity, methodology, and the importance of verified evidence, rather than sensational claims. Graduate students and early career scientists contributed models exploring alternative explanations, providing fresh perspectives. Real-time data analysis allowed rapid identification of subtle shifts in the signal, refining ongoing predictions. Minor energy variations hinted at periodic cycles, providing further clues about the object's behavior. Researchers emphasized patience, noting that understanding the anomaly fully could require months or years of observation. International conferences focused on collaborative methods for studying such unprecedented phenomena. Observatories continued to expand monitoring across multiple wavelengths, including optical, radio, and X-ray. Analysts compared historic and current data to identify persistent trends or changes over time. Findings suggested the object's energy output was stable, yet displayed small detectable modulations. Simulations of plasma and dust interactions provided partial explanations for these subtle variations. Researchers noted that studying such unique phenomena could lead to revisions in theoretical astrophysics. Peer-reviewed journals documented methodologies, ensuring transparency and reproducibility for future investigation. Observatories coordinated to monitor the object continuously, increasing confidence in the data. Analysts emphasized evidence-based interpretations, avoiding speculation about non-scientific possibilities. The anomaly inspired curiosity-driven research programs for students and young scientists worldwide. Each new observation added depth to the understanding of its energy patterns and environmental interactions. Investigators stressed ethical communication with the public, highlighting science over sensationalism. Minor gravitational disturbances detected suggested the object's influence extended beyond its immediate surroundings. Researchers used these observations to refine models of its potential internal structure. Observatories worked together to validate measurements, ensuring alignment across instruments and geographic location. Long-term monitoring revealed the anomaly's energy pulses exhibited gradual shifts, suggesting dynamic processes. Researchers detected slight periodicity in the emissions, hinting at an internal cycle within the object. The pattern was consistent across multiple observatories, confirming the signal was not an artifact. Subtle interactions with surrounding interstellar matter became more apparent, revealing a complex influence. Scientists emphasized that these observations were part of an evolving process, not indicating artificial activity. Modeling the anomaly's interactions suggested previously unconsidered forms of energy transfer in star systems. These findings could influence understanding of stellar formation, energy emission, and cosmic evolution. Analysts noted correlations between energy shifts and nearby dust cloud density, revealing feedback effects. Long-term simulations explored mechanisms for the anomaly's behavior, guiding future observation strategies. Scientists stressed that the full explanation would require months or years of data collection and analysis. Historical archive review suggested minor signals in the past may have been early indicators of this phenomenon. Researchers carefully documented these correlations to ensure reproducibility and methodological rigor. International collaboration remained essential, allowing teams to cross-validate observations in real time. Peer-reviewed publications outlined methodologies and preliminary interpretations while emphasizing ongoing investigation. Students and early career scientists contributed to modeling efforts, gaining experience in research. Observatories continued multi-wavelength observations, including radio, optical, and X-ray, to capture a complete picture. Minor variations in signal strength suggested the object might be slowly evolving, offering clues about internal processes. Laboratory simulations attempted to replicate energy modulation patterns, providing instructive results. Researchers emphasized that these simulations informed hypotheses without asserting conclusions beyond verified data. Real-time data sharing enabled rapid adjustments to observation schedules based on emerging trends. Analysts compared the anomaly with other known phenomena, identifying similarities to refine classification. Early models suggested the object could represent a new class of naturally occurring stellar systems. Public science programs highlighted discoveries responsibly, emphasizing methodology and exploration. The anomaly's discovery reinforced the need for continuous observation of even ordinary star systems. Minor gravitational influences on nearby objects were measured, suggesting mass distribution unique to this phenomenon. Researchers highlighted how subtle cosmic interactions can produce detectable signals. Each new measurement refined theoretical models, leading to a deeper understanding of stellar behavior. Simulations incorporating interstellar dust, magnetic fields, and energy transfer produced accurate predictions. Citizen science programs contributed responsibly to pattern recognition and data verification under expert supervision. Analysts emphasized evidence-based interpretation and avoided speculation about extraterrestrial origins. Coordination between observatories ensured consistency, verification, and comprehensive monitoring of the phenomenon. Minor periodicity observed in the signal provided additional constraints for theoretical modeling. Findings suggested the anomaly might operate under natural physical processes, yet to be fully understood. Scientists emphasized that patience and careful observation were essential for accurate conclusions. Educational content highlighted the discovery process, focusing on curiosity and rigorous data analysis. The object's persistence and subtle variability underscored the universe's complexity and capacity for surprise. Observatories planned long-term campaigns to track potential evolution over months or years. Analysts used these data to refine models predicting energy emissions and interactions with the environment. Cross-validation across instruments reinforced the reliability of observations and reduced potential errors. Research teams published preliminary findings while noting the need for ongoing data collection. Simulations indicated that energy modulation might arise from internal dynamics or interactions with nearby matter. Minor gravitational shifts suggested that the object's influence extended beyond immediate surroundings. International collaboration remained critical to maintain transparency and accuracy.